Okay, let's go ahead and walk through the conjectures for Chapter 4, Properties of Triangles. The first conjecture that we have is conjecture number 17, the triangle sum conjecture. And all we're saying here is as you move the triangle around, you can see the angles changing. All we want to show is that the sum of the three angles will add to 180 degrees. So if you come up to number, calculate, we'll just take angle B plus angle C plus angle A and show that this sum will always be 180 degrees. Conjecture number 18, the isosceles triangle conjecture. We have measured out that the sides are congruent, and we know if it's isosceles then the base angles are also congruent. So what we'll do is we'll just highlight these angles and measure the angles and show that angle CDA is congruent to angle ACB. Conjecture number 19, the converse of the isosceles triangle conjecture. If we know that the base angles are congruent, that means that the opposite sides are also congruent. So if you highlight just those opposite sides, you can deselect and select those two and measure those sides or measure those lengths. You will see that segment BA and BC are congruent. Conjecture number 20, the equilateral equiangular triangle conjecture. What we're going to show here is that if you have an equilateral triangle, which has been measured out, then the angles are also congruent. And the triangle is also equiangular. So if I measure those angles, you can see that each angle has a measure of 60 degrees. So equiangular triangles are equilateral, and equilateral triangles are also equiangular. All right. Next conjecture, conjecture number 21, the triangle inequality conjecture. And this one says that the sum of any two sides of a triangle must be greater than the third side. Okay, so what do we want to show here? We're going to open up a text box. So if you select the text tool on the left-hand side, and you click and you drag open a text box, we can start to click on stuff. So let's click on this first one. And what this one says is it says the measure of segment AB plus, we don't want to add that. The segment AB plus the measure of segment CA is going to be greater than, and I'm just typing this on the keyboard, is going to be greater than the third side. It's going to be greater than BC. Go ahead and press enter to drop to the next line. We're going to show that the measure of segment CA plus the measure of segment BC has to be greater than our third side, which in this case is AB. And then lastly, we're going to show that AB plus BC must be greater than our third side, which in this case is CA. Okay, and that is our triangle inequality conjecture. What's neat about this is as you hover over the data here, you can see where the data is coming from. Also, as you move the triangle, you can see how the numbers break out. But just know that you can never make a triangle where this sum is smaller than the third side. The sum of any two sides must always be greater than the third side. Conjecture number 22, the side angle inequality conjecture. This simply states, and you can just observe it here, that if you take a look and look for the smallest, or excuse me, the largest angle, and you go across from that, you go opposite from that, you will get the largest side. Opposite the smallest angle, so if I go across from that, will be the smallest side. For this one, you can just take a picture of what's here and paste it into your dictionary. Conjecture number 23, the triangle exterior angle conjecture. What this states is the exterior angle of a triangle, the measure of this angle here, is always going to be equal to the sum of the remote interior angles. So remote meaning that they're far away, interior meaning that they're inside the triangle. So if I were to calculate the sum of the remote interior angles, that's always going to be equal to my exterior angle. And you can move the triangle to see that as well. Okay. Conjecture number 24, side, side, side. If I give you a fixed side and a fixed side and a fixed sides, how many triangles can you make? And I just want you to show me that you can only make one possible triangle. So pull these together and show that there's only one triangle to be made there. The next conjecture, conjecture number 25, you're given a side, an angle, and a side. So first I have to move this side onto the angle, and then this one I can go anywhere with it. I can go in any direction. So if I have a fixed side, a fixed angle, and a fixed side, there's only one triangle that I can make, and it would be right there. The next conjecture, the side-side angle non-congruence conjecture. What we're going to show here is we're going to show two triangles. We have a fixed side, and a fixed angle. When I move this fixed side to this point, you can see we have one triangle here. And as this rotates through, we'll get a second triangle that connects here. Okay. So those are the two triangles that you can show for the side-side angle non-congruence. The next conjecture, angle-side angle. So I have an angle, a side, and an angle. You'll notice you can't change the angle here. So there's only one triangle that can be made. Angle, angle, angle. By pulling one of these points, you can see there is an infinite number of different triangles you can make, even if the angles are fixed. Okay, they all have the same shape, but all the sizes will be different. Conjecture 27, angle, angle, side. So if I have a fixed angle, and a fixed side, how many triangles can I make? And as you pull out angle C, you can see there is only one triangle that can be made. The last conjecture, the conjecture that we learned about today, was the vertex angle bisector conjecture. So if you bisect the vertex angle of an isosceles triangle, what happens? What happens is that it intersects the opposite side at 90 degrees. If you grab the marker tool and you pull into the angle, you click and you pull in, it'll snap to 90 degrees. The other thing that you're going to want to do is measure lengths DC and DA. So if I measure those lengths, let's see, grab the wrong one. So I have CA as the total. So I have DC, and I want to measure just AD. Measure length. You can see that those are equal. Okay, so what do we know? We know that if this bisects the vertex angle, this creates an altitude going from the vertex perpendicular to the opposite side. This also creates a median going from the vertex to the midpoint of the opposite side. And those are the conjectures for chapter